Hello and welcome to another computational geometry program. So here we have a program focusing on the variance of the hidden set problem. Now there's three variants: hidden set, hidden vertex set, and R hidden guard set. I'll get to what each of those mean in a minute, but first I want to describe what a histogram polygon is, because unlike my other programs, there's a pretty rigid input set because these problems are NP-hard for general simple polygons. So the algorithms I'm going to present are specifically for histogram polygons. Histogram polygons, or orthogonal monotone mountains, are shapes which are orthogonal, meaning that they have all their angles are either 90 degrees or 270 degrees, so it's always like a right angle, or orthogonal. And so that means it's comprised of only horizontal or vertical edges without loss of generality. And we have another part, monotone. That component regards the ability to throw a line through any part of the shape, right? So in this case it's X monotone. Meaning that any line perpendicular to the X direction passing through it only passes through it once. Or you could also say it's made of two monotone chains. So this is an upper chain, and it's always increasing in the X direction, or not making any movement at all. So it's monotone. And then the other chain does the exact same thing. Now the other component is the mountain part. So monotone and mountain are kind of the part that go together. It's comprised of two monotone chains, such that one of those chains is only one side, or the base. And the idea is that this base is it spans basically the entire shape. It's the leftmost point in that X direction, because it's X monotone, and it also contains the rightmost point in the X direction. Now, for that's the definition of a monotone mountain. Of a histogram polygon in general, by adding in the orthogonal element. This program allows you to pencil in pretty much any histogram you would like. You control click to add in a point on an edge, and then you can select these corners and drag them around. You can't violate monotonicity. That's the one rule. So no playing around like that or anything. It's pretty defensively programmed. And the idea is, once you have that histogram polygon penciled in, we have our three different quantities that you can look through. Now the hidden set is just a set of points such that no two can see each other, or a set of points that are hidden from each other. The hidden set algorithm was actually developed by myself and my friend Eric too. And basically the algorithm iterates through the horizontal edges of the histogram polygon, going here to here to here to here. And the idea is that we can always place points at the middle of these horizontal edges, with one major exception. If these edges are collinear, they're parallel with each other. So I'm not 100% sure that those are exactly collinear. We'll see when we run the algorithm, but the idea is we need to keep track of all the possible collinear horizontal edges that are a threat. So for these, some of these are pretty close. If we brought that down maybe a little, they'd be pretty close, but because there's an edge below here, we don't actually have to worry about that. So as a result, the stack, we maintain a stack where the top of the stack is the highest Y level that we're dealing with. And the idea is that if the current edge is lower than that Y level, we pop it off. If it's equal to that Y level, then we know that there's the threat. and if it's greater, then we just push the current y level onto the stack, and we add the point to the set. And we keep popping off until we get that equality, or we get that it is above all the other ones, and then we just throw it on. So, and the idea is just so that we are keeping track of all of the possible points, edges, which can cause a problem in terms of placing hidden points on the midpoints of those horizontal edges. So I'm going to run through the algorithm. Hopefully it makes more sense on the run through. Puts one there, but then it was, this is lower, so then it popped it off. And as you can see, these were collinear. So when the stack was up to here, we got to this point, this was popped off, and then these were equal, so then we continued onward. So that's the hidden set algorithm. And it finds a hidden set, a maximal hidden set. And we know this to be the case because of another problem called convex cover, and we showed that our algorithm can find both of those quantities. But for the case of this program, we're just dealing with hidden set, so we're not going to be worrying about that. Now for hidden vertex set, I used ideas from Bajuelos et al. Their paper called Hiding Points in Spirals and Histograms. It's in Spanish, so in the Spanish name is Escondiendo Puntos en Espirales Histogramas. Not fluent in Spanish, so apologies if that's mispronounced. But so this paper goes through the spiral polygons and histogram polygons, and claims that when they're in general position, the only difference between hidden set and hidden vertex set, which is hidden set but all of the points have to be vertices, is that putting the points at these bottom sides are impossible. It's going to cause issues. So you'll never put vertices there, so it's the vertex count when in general position is literally just equal to the total number of reflex vertices minus the number of these plus one minus the bottom sides. And so the result of that is we can edit our algorithm to work for vertex set by placing them in the corners if possible, and if they're at these bottom sides here, we just don't place, we'll still do the same operations, but we just won't place any vertices there on those. So if we run through, we place them on those corners. As you can see, there's been no issues so far. This one it's choosing the left corner, elsewise it would see into here, but it's very slight, so it's kind of hard to tell. So that's the hidden vertex set, very similar to our algorithm, but using the Bajuelos insights to advance to this other problem, more constrained version of the problem. And now the most different of them is the hidden guard set. So in this case, we're not really trying to get as many as possible, but actually as few as possible. The minimum hidden guard set. So all of these have to be hidden from each other, but they have to guard the whole polygon. Now, hidden set does this in terms of it's always going to cover the entire polygon. You can see all of the points, but we want a minimum set, not a maximum set of this type. So we've also constrained the type of vision. This is not my algorithm. This is I believe it's Hurfar and Bagheri. Their minimum hidden guarding of histogram polygons. And basically their algorithm maintains this idea of a pyramid, and the idea is that if you're right below the top of a pyramid, you could place a hidden guard at the bottom of it, and then it'll see that entire pyramid, and that's under orthogonal vision. Orthogonal vision means that 2 points can see each other if the axis aligned rectangle between them doesn't intersect the boundary. So I'm just running it right now so that I can better explain this idea of orthogonal vision. So the idea is that this point and this point, if you drew the orthogonal rectangle, then it's going to intersect the boundary. So in normal vision, yeah, they do see each other, but in orthogonal vision, they can't, because this rectangle passes just above that edge. And the same with these guys, the rectangle passes through that edge, and so on. And the idea is that these are now hidden from each other in terms of orthogonal vision. And they also see the entire polygon in terms of orthogonal vision. So this guy sees all of this bottom area plus this area and then this area. So this is like a pyramid. What it sees, it's like a staircase. They refer to it as a pyramid because it doesn't necessarily have to be one-sided, it could be two-sided. Such as in this case, we're going up here and then down there. And the idea behind this algorithm, in terms of implementation, it was decently different. We mostly are keeping track of this top edge when we get to a overhang like this. Anytime we have one of these, we can throw the guy at whatever horizontal position we've kept track of last in terms of these guys. And that kind of, these anti-knobs, as they're referred to, are the Y level of those kind of separates the pyramids off. So the idea is any point in here can't see any point that's just above that line. And the idea is we just place our hidden guard there, and then we're done. So that pretty much wraps up my hidden set suite for histogram polygons. As I mentioned, these are NP-hard problems in the general case. So working towards more subclasses will be great. In particular, monotone mountains in general, I think, are within scope. And yeah, hopefully we can get some more algorithms and better visuals for this problem, because it's very interesting. Yeah, so this is my project, and I hope you like it. Have a great day.